नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार द्विशेट्टी, फैकल्टी ऑफ ऑप्टिकल इंस्ट्रूमेंटेशन। मैं आप सब लोग को यहाँ सुबह सुबह स्वागत कर रहा हूं हमारा सेशन पर। बहुत वेटिंग सेशन है, अवेटिंग सेशन है, ऑप्टिकल इंस्ट्रूमेंटेशन। दिस सब्जेक्ट इज फॉर द गेट इंस्ट्रूमेंटेशन स्टूडेंट्स। मुझे पता है बहुत सारा गेट इंस्ट्रूमेंट स्टूडेंट्स ये सब्जेक्ट का रिविजन के लिए वेट कर रहे हो। सो आज हम डिस्कस करेंगे ऑप्टिकल इंस्ट्रूमेंटेशन का one shot lecture on optical sources if possible on optical fibers. ओके, सो जितने भी लोग लाइव में हैं मुझे एक बार वॉइस कंफर्मेशन कर दीजिए, ऑडियो वीडियो सब कुछ क्लियर या नहीं। ओके, आज हमने ऑप्टिकल इंस्ट्रूमेंटेशन में क्या डिस्कस करेंगे। अगर आपका गेट का इंस्ट्रूमेंटेशन का वेटेज देखे तो 4 to 5 मार्क्स का वेटेज है ऑप्टिकल इंस्ट्रूमेंटेशन पर। इसके लिए इतना ज्यादा बुक्स पढ़ने की जरूरत नहीं है, केवल बहुत सारा कम टॉपिक्स है। लेकिन यह सोच होता है इंस्ट्रूमेंटेशन बच्चों के लिए, हमारा कोर सब्जेक्ट जो है, हमारा कोर सब्जेक्ट्स के लिए कंटेंट कहाँ मिलेगा। सो आपको ये पता होना है, सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन का ऑलरेडी हमने बेहतरीन लेक्चर्स डिस्कस किया था। सो वी हैव डिस्कस कंफर्टेबल लेक्चर्स ऑन सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन. Now we are going to discuss the optical, and soon I am going to start the measurements also. In measurements also you are going to get a good content. Okay, so आज ऑप्टिकल इंस्ट्रूमेंटेशन का लेक्चर 1 है. So first of all let us see the syllabus. ऑप्टिकल इंस्ट्रूमेंटेशन का बहुत सारा कंटेंट है, सो इसका सिलेबस नोट करेंगे. फर्स्ट ऑफ ऑल द सिलेबस इज ऑप्टिकल सोर्सेस. सो अंडर द ऑप्टिकल सोर्सेस हमको क्या आएगा, अंडर द ऑप्टिकल सोर्सेस हमको मिलेगा एलईडी, लाइट एमिटिंग डायोड, and LACR, laser, etc. So these are the topics that we are going to cover under the optical sources. Okay, and next topic is ऑप्टिकल डिटेक्टर्स. एक्चुअली इसके बीच में जो आएगा ऑप्टिकल फाइबर आएगा. सो बेसिक्स ऑफ ऑप्टिकल फाइबर, बेसिक्स ऑफ ऑप्टिकल फाइबर और फाइबर ऑप्टिक की सेंसिंग है. नेक्स्ट इसके बाद ऑप्टिकल डिटेक्टर्स आएगा. ऑप्टिकल डिटेक्टर्स टॉपिक्स में हमको मिलेगा एलडीआर एंड फोटोडायोड एक्सेट्रा. ये एक्सेट्रा आल्सो इंपॉर्टेंट, दीज आर द रेगुलरली आस्क्ड टॉपिक्स. नेक्स्ट इसके बाद जो हमको मिलेगा बेसिक्स ऑफ इंटरफेरोमेट्री, बेसिक्स ऑफ इंटरफेरोमेट्री. next last topic that is also included, that is UV visible IR spectrometry or spectrophotometry. And last one is mass spectrometer. क्या है last one? The last one is the mass spectrometer. So now if you see the topics I am going to cover today, I will try to cover this and this for today. Okay, so please note down the list. जल्दी से ज्वाइन कर लो बेटा. आ रहे वॉइस? या सॉरी राजश्री, अभी वॉइस आ रहे? कब से नहीं आ रहे वॉइस? ओके ओके, अभी वॉइस आ रहे हैं ना? द वॉइस इज क्लियर नाउ? बिगिनिंग से आ रहे हैं, अभी नहीं आ रहे? अभी क्लियरली आ रहे वॉइस? कब से नहीं आ रहे वॉइस? वीडियो पहले से आ रहे? अरे यार, मैं इसलिए मैं पूछा पहले से ही। अभी क्लियर आ रहा है? कब से नहीं आ रहा है? क्या था? So we have discussed comfortable lectures on sensors and distribution. Sorry. I think from the last 5 minutes it has not come. So let me explain once again. So this is a light electromagnetic wave. So if you see the electromagnetic waveform, so the electromagnetic waveform lambda is increasing from left to right. The lambda wavelength is 380 nanometers to 780 nanometers. So lambda wavelength is 380 nanometers to 780 nanometers. This is the wavelength of the visible radiation. हमारा जो कलर से हम जो कलर्स दिख रहे हैं. सो अभी बीच में मुझे पता ही है, अगर कुछ वॉइस का डिस्टर्बेंस है तो मुझे जल्दी बताइए यार. अभी वॉइस क्लियर है ना? यस. थैंक यू यार. चलो, now let us see here. So lambda is the wavelength in nanometers. For cosmic radiation it is 1 picometer, and for radio waves it is 1 kilometers. So left to right, what is happening? Left to right, the lambda is increasing. So if the lambda is less, energy will be more. If the lambda is more, energy will be less. So here, the shorter the wavelength, higher the energy. Try to understand. The shorter the wavelength it is having, the higher the energy. So for example, if you see the lambda of X-rays here and the lambda of visible here, if you check, the lambda of X-rays is shorter. Whereas energy of the X-rays will be greater. Okay, so energy of the X-rays is greater. So penetrating power of the X-rays is greater than penetrating power of the visible radiation. Penetrating power of the X-rays is greater than the penetrating power of the visible radiation. So try to understand that. So that's why X-rays are highly emerging, highly penetrating, right? The more is the wavelength, the less will be the energy. The lesser is the wavelength, the higher will be the energy. So the penetrating power of X-rays will be more than the penetrating power of visible. So X-rays have more penetrating power. Try to understand this. X-rays have more penetrating power. X-rays have more penetrating power than visible. X-rays have more penetrating power than the visible. Okay, na? So please have this understanding. X-rays are having more penetrating power than the visible. So this is what how the mathematics I have explained, where h is the Planck's constant. So 6.625 into 10⁻34 joules. ऐसा होना है, अगर बीच बीच में क्या है ना, कभी कभी क्या होता है ना, बच्चे लाइव में रहते हैं लेकिन कुछ ना कुछ रिस्पॉन्स ही नहीं देते. Okay, students will be there in the live, but like they won't give response. They want only, they won't give response. So in those times, what I will do this type of tricks. I will switch off the mic sometimes for 5 seconds, 10 seconds. Then automatically बच्चे मुझे response देते हैं, सर माइक ऑफ है, ऑडियो नहीं आ रहे. जो लोग गुड मॉर्निंग भी नहीं बोलते, डायरेक्टली बोलते मॉर्निंग है, गुड मॉर्निंग भी नहीं बोलते क्लास को, सो डायरेक्टली आके बोलते हैं सर माइक नहीं है. हाँ चलो चलो my dear दोस्तों. So if you see now, so this h is the Planck's constant, that is 6.625 into 10⁻34 joule second. So 1 joule is equal to 10⁻7 ergs. So 6.625 into 10⁻27 आएगा, 1 joule के बोल के 10⁻+7 आएगा. If you substitute 10⁻7 ergs आएगा. And from that 1 electron is equal to 1 electron volt is equal to 1.6 into 10⁻19 joules. So 1 joule is equal to 1 by 1.6. So if you substitute, I'm going to get 4.14 into 10⁻15 electron volts second. 4.14 into 10⁻15 electron volts second. So now, so energy, suppose if you take energy calculation, suppose a question is given, a light of 638 nanometers. So that is a wavelength of a green helium neon laser actually. So this is a helium neon laser wavelength. So if you see this particular wavelength, 638 nanometers, if it is incident on a semiconductor material, so what is the wavelength का energy? जो light का है ना, light का energy कितना होगा? So lambda is 638 nanometers, h is equal to 4.14 10⁻15 electron volt second. C is the velocity of light is 3 into 10⁸ meter per second. So in the place of h, I can write it as 4.14 into 10⁻15 electron volt second. C is a 3 into 10⁸ meter per second. So lambda 638 into 10⁻9 meters cancel, second cancel. So now I'm going to get energy is equal to 1.946 electron volts. That means light के पास कुछ ना कुछ energy है. आपने पढ़ चुका है semiconductors में energy gap का भी कितना है energy, that is 2 electron volts. So the light of 638 nanometers is having, green light is having an energy of 2 electron volts, which can trigger electrons of ground state to move to the higher state of a semiconductor which has an energy gap of 2 electron volts, which has energy gap of 2 electron volts. So now let us move. So now let us take the sunlight. If you see the sunlight, so this is our sunlight. So सुबह सुबह हम देख सकते हैं sunlight. Sunlight contains lambda 275 nanometers. So actually sunlight कैसा होगा? So if you see the electromagnetic spectrum, so this is a UV radiation, so this is the visible radiation, and this is the IR radiation. So this is our visible, and this is our IR, and this is the UV. So sunlight contains these three parts, but not fully. So if you see, that will contain, so mid UV to mid IR. So it contains from mid UV to mid IR. So it contains from here to here. So this wavelength is 275 nanometers to 2750 nanometers. 275 nanometers to 2750 nanometers. Got it, Rajashree? Bharat Kumar, is it clear? Mid UV to mid IR. So it starts from mid UV, complete visible, and mid IR. Mid UV to mid IR. So it does not contain this part. This part is not present. This part is also not present. So this is far UV, it is not present. And the far IR is also not present. But this near UV is present. This complete visible is present. And near IR is present. So if you see the sunlight, sunlight contains what actually? So sunlight, if you see, far UV, mid UV, near UV, visible, near IR, mid IR, far IR. So sunlight contains far UV, it contains no, mid UV it contains, near UV it contains, 100% visible light it contains, near IR it contains, mid IR it contains, far IR it does not contain. So please make a note of these points. Sunlight does not contain far UV and far IR. Far UV and far IR. Done? Chalo. Now let us see the UV sources. So these are the different types of UV sources. So how the UV light is going to be generated? So when the UV light electron is going to hit, when the electron hits the gaseous molecule, when the electron hits, and 2 electrons will be coming out, and in addition to this, UV radiation is going to be emitted out. In addition to this, what is going to happen? UV radiation is going to be emitted out. One electron hits gaseous molecules and the gaseous molecule becomes like an ion, and 2 electrons will be coming out. So in the gaseous molecule, this is the status of the gaseous molecule. So if you see the gaseous molecule like this, so this is a nucleus and this is outer orbit gaseous molecule. So outer orbit gaseous molecule will be having some energy less. So now from this point of view, some electron is coming and hitting. So this is the electron which is roaming in this orbit. This electron which is roaming in this orbit. So when electron comes and hits, so this electron comes and hits the gaseous molecule. So the gaseous molecule become like ion, 2 electrons are going to be emitted. So when this electron ejects, then what happens? In addition to that, UV radiation is also going to be emitted. So UV radiation is also going to be emitted. So that's why UV radiation is coming because of the discharge of electron. इसलिए हम उसको बोलते हैं electric discharge process बोलते हैं. So this process is called as electric discharge process. So UV light is going to be generated in what purpose? In a process of electric discharge. It is going to be generated in electric discharge process. Electron discharge होने की वजह से electric discharge process. Electron discharge होने की वजह से हो रहा है, so उसको हम बोलते हैं electric discharge process बोलते हैं. So from the hydrogen gas, if electron is emitted, so then it is called hydrogen lamp, and from the deuterium gas it is emitted, it is called deuterium lamp. From the mercury gas, mercury lamp. So sun is also a source of electricity. Sun is a source of electricity. Sun is a source of electricity, my dear. Okay, चलो, is it clear? जितने लोग लाइव में मुझे कंफर्मेशन कर दीजिए बेटा, क्लियर या नहीं. चलो, एंड द यूवी लाइट डिटेक्शन के लिए हमारे पास और एक है, सो दैट इज कॉल्ड फोटो एमिसिव सेल. सो उसको हम बोलते हैं फोटो एमिसिव सेल. सो फोटो इलेक्ट्रिक इफेक्ट भी बोलते हैं और फोटो एमिसिव सेल्स भी बोलते हैं. चलो, नाउ लेट अस गो फॉर द नेक्स्ट. Visible sources. So if you see the visible sources, what are the visible sources? So visible radiation comes in the 380 nanometers to 780 nanometers. So जो भी हमको कांति visible में आएगा उसको हम visible radiation बोलते हैं. So what are the visible sources? Tungsten filament bulb is a visible source. Tube light is a visible source. Sunlight is a visible source. Candle light is a visible source. LED is also visible. Laser is also visible. Some of the lasers are visible, not all the lasers. So LED can be taken as spontaneous emission. So LEDs can be taken as spontaneous emission, whereas a laser can be taken as stimulated emission. Laser can be taken as what? Stimulated emission. Please make a note of this. Light measures light principles. Okay. चलो, नेक्स्ट इसके बाद आएगा. सो हाउ द एलईडी वर्क्स. सो इफ यू सी द एलईडी, लाइट एमिटिंग डायोड. सो वन ऑफ द इंपॉर्टेंट है विजिबल सोर्सेस में एलईडी के ऊपर भी क्वेश्चंस आने की चांसेस ज्यादा है. सो लेट अस सी द एलईडी हाउ इट वर्क्स. सो एलईडी वर्क्स इन द फॉरवर्ड बायस, दैट इज वेरी क्लियर. ओके, सो एलईडी के पास कुछ मटेरियल्स है. सो एलईडी इज नॉट गोइंग टू बी डिजाइन्ड बाय डिफरेंट ऑल द मटेरियल्स. एलईडी कंस्ट्रक्ट्स, LED comes because of certain materials only. So the materials are, we can take it as gallium arsenic, gallium phosphide, gallium indium arsenic, gallium sulfide. So these are the semiconductors. Okay, so gallium arsenic, gallium phosphide, gallium indium arsenic, gallium sulfide. So these are the semiconductors materials. Okay, so now if you see this is the energy structure. So this is a valence band. So this is a conduction band. So this is a energy 1 E1 and this is energy level E2. So energy gap I can take it as E2 minus E1. The units are electron volts. So gallium arsenic, gallium phosphide, the material is waiting like this. So these are the electrons. The electrons are waiting here. So when the current hits now, so what is the input that we are going to give for this gallium arsenic LED is the current. So this is a gallium arsenic. So the gallium arsenic will emit the light once the current comes. So now when current comes here, the current enters and the current makes a gallium arsenic, so the light will going to be emitted. Light is going to be emitted. So the input is the current. So when the current is given, so now the valence band electrons are going to take that energy, and the electrons move from the valence band to the conduction band. Electrons move from the valence band to the conduction band. That's fine. So, but the lifetime here is almost 10 to the power minus 8 seconds. So they can sustain here only up to 10 to the power minus 8 seconds. They can sustain here up to 10 to the power minus 8 seconds only. They cannot sustain more than that. The lifetime is very, very less. So 10 to the power minus 8 seconds के बाद वो क्या होगा, वहां से नीचे गिर जाएगा, वहां से नीचे गिर जाएगा. So 10 to the power minus 8 seconds over होने के बाद, so जो भी electrons है ऊपर गया, so these electrons are going to come down. So these electrons are going to fall down. So this part here, this is absorption. So current taken and the electrons are moving up. So this is what we call as absorption. So this is what we call as absorption. In absorption, I am going to have electron hole pair combination. Electron hole pair combination. Okay, electron hole pair combination. So this is what we call as electron hole pair combination. In electron hole pair combination, I am not going to get anything. Light का possibility नहीं है, लेकिन but here if you see, after 10 to the power minus 8 seconds, these electrons are going to fall down and falling into this. So electrons are coming and occupying this. So this is what we have now. Light is coming and hitting. So electron is merging with the hole. So this is what we call as electron hole pair recombination. Absorption lo electron hole pair combination, but light is going to be generated in absorption electron hole pair combination. So in emission, electron hole pair combination gives, so if you see this, electron hole pair recombination. Electron hole pair recombination gives the emission of the light. Okay, so try to understand that. So light emission is possible not in electron hole pair combination. Light emission is possible only in electron hole pair recombination. So that's the point we have to understand. So 10 to the power minus 8 seconds होने के बाद, so these electrons are going to come down. So it is going to happen electron hole pair recombination. So electron hole pair recombination, so will be like this. Energy gap is E2 minus E1 h nu. So जो भी light बाहर आ रहा है, so that light will be having a wavelength. So the energy of the photon is given by hc by lambda. So what is that wavelength? So that wavelength is equal to hc by lambda. Okay, so this particular lambda reflects a color. This particular lambda reflects as a color. Is it clear, my dear? So this lambda reflects a color. Sure. Next, so these materials are called direct band gap materials. Why? Because the journey is directly from top to bottom. The journey is directly from top to bottom. So these materials are called direct band gap materials. So if you see the direct band gap materials, because of the direct band gap materials, जो भी light आ रहा है, वो light is not having coherence nature. They are not in phase because at different intervals of time the light photons are going to come. So the characteristics of LED, if you see, so this is a spontaneous emission I told you. So in spontaneous emission is happening in electron hole pair recombination. Spontaneously 10 to the power minus 8 seconds के बाद electrons नीचे जा रहे हैं. And this is a single step transfer. In one step the electrons are falling down. Next, the radiative recombination, I am going to get the light. So when the electron comes from the high energy state and falls down, I am going to get the light. So there are different phases. Different phases means they are incoherent. Different directions means they are dispersive light. Different lambdas means it's a non-monochromatic light. So non-monochromatic light. So please make a note of these points. जितने लोग लाइव में हैं प्लीज कंफर्मेशन कर दीजिए. नोट कर दिया? So that is the radiated recombination, quite opposite to the laser. So laser is different. LED is different, laser is different. Laser light, if you see, laser light is coherent. Laser light is focusing. Laser light is monochromatic. Monochromatic. So coherent, focusing and monochromatic. Chalo, now let us see other points. So if you see the fundamental differences between the LED and the PN junction. PN junction diode is also same, right? In PN junction diode also we are having energy gaps. But the point here is, in PN junction we are having the metastable state in between. Okay, general PN junction diode, we are having 3 energy levels. So in between there is a metastable state. Here there comes a metastable state. So this is the E1, this is the E2, this is the E3. So this is the E1, this is the E2, this is the E3. So E1 is the ground state, E3 is the high energy state, E2 is the metastable state. So what is metastable state? Metastable state is the intermediate states where its lifetime is 10 to the power of minus 5 seconds. So here the lifetime was 10 to the power of minus 8 seconds. Here the lifetime is 10 to the power of minus 5 seconds. So in PN junction diode, what happens? The electrons which jump to the high energy state, they will come to the intermediate state for some time. They will stay there and then it will come relaxfully here. So इसकी वजह से क्या होगा? जो इलेक्ट्रॉन ऊपर से नीचे आ रहा है उसका पूरा एनर्जी कांति के रूप में नहीं आएगा, थोड़ा हीट रूप में आएगा. So if you see now, so this is how it is going to happen. So electron hole pair combination में current की वजह से light आ रहा है. So that is a LED, but this is not LED. This is PN junction diode. Sorry. In PN junction diode, what actually comes here? What actually comes here is heat. What actually comes here is heat. IN407 is heat. Got it? So now if you see indirect band gap materials. So these materials are indirect band gap materials. Why? Because electrons are not coming from direct from higher to lower. They are crossing through some intermediate state called metastable state. So if you see, this is the E1, this is the E2, this is the E3. So electrons are moving from the ground state to the higher energy state. From there they are falling down to the metastable state. So from the metastable state they are coming down. So in this process what is going to be generated is heat. Okay. So now if you see the fundamental differences between LED and the PN junction diode. So LED का materials है gallium arsenic, gallium phosphide, gallium sulfide, gallium indium arsenic, and PN junction diode का materials है germanium, silicon, selenium. Next, these are called direct band gap materials. So these are called direct band gap materials. So these are called indirect band gap materials. So these are direct band gap and these are indirect band gap. Next, this is LED is a forward bias. So LED is a forward bias. PN junction diode is also forward bias. PN junction diode is also forward bias. So this is here the radiative recombination rate is more. That means radiative recombination means which emits the light. So which does not emit the light, that is a non-radiative recombination. So non-radiative recombination is more. So that means heat. So this comes the heat. Heat is more. It will be so probability of light here is more than the probability of heat. Here probability of heat is more than probability of light. This is a single step transfer, this is a two-step transfer. So now let us take the time interval between the two successive radiative recombinations. That means suppose if you take LED, एक इलेक्ट्रॉन ऊपर से नीचे गिर गया, नेक्स्ट और एक इलेक्ट्रॉन ऊपर से नीचे गिर गया, ये दोनों के बीच में कुछ टाइम डिफरेंस होगा, लेकिन ये टाइम डिफरेंस बहुत लेस होगा, सो दैट द रेट ऑफ फास्टेस्ट विल बी देयर. फास्टेस्ट रेट से वो इलेक्ट्रॉन्स नीचे गिर जाएगा. सो टाइम इंटरवल बिटवीन द टू सक्सेसिव रेडिएटिव रिकॉम्बिनेशन इज TRR. So this is the TRR. So this is the TRR. So TNRR means time interval between the two successive non-radiative recombinations. इसका इन्वर्स करो, हमको 1/TR हमेशा रेट ऑफ रेडिएटिव रिकॉम्बिनेशन आएगा, एंड इसका इन्वर्स करो 1/TNRR करो. सो उसका तो क्या होगा, इसका रेट ऑफ नॉन रेडिएटिव रिकॉम्बिनेशन होगा. सो दिस इज 1/TRR, 1/TNRR. So this is the rate of radiative recombination, this is the rate of non-radiative recombination. So this comes as rate of radio recombination, this comes as rate of. So LED में क्या होगा? LED में rate of radio recombination will be more. So for LED, rate of radio recombination will be more, whereas rate of non-radio recombination will be less. So for LED, this is a situation. Rate of radio recombination will be more, rate of non-radio recombination will be less. And for LED, time interval between the two successive radio recombination will be lesser than the time interval between the two non-radio recombination. So TRR will be lesser, TNR will be greater. So this is for LED. This is for LED. But whereas if you go for the PN junction diode, so this is for PN junction diode, for PN junction diode. So for PN junction diode, so TRR and TNRR, if you check, time interval between the radio recombination will be more, time interval between the two successive non-radio recombinations will be less. Next, rate of radio recombination and rate of non-radio recombination, if you check, rate of non-radio recombination will be more. So this is our PN junction diode. So for LED is that, for PN junction diode is that. Okay, so please make a note of these points. Chalo. So now if you see some questions here, for LED, if you see, for light emitting diode, TRR will be lesser than the TNRR, RRR will be greater than the RNRR. So R total, if you see the total rate of radio recombination, that I can take as RRR plus RNRR. So if you see RRR, rate of radio recombination ka inverse karo 1 by TRR, rate of non-radio recombination 1 by TNRR. So total rate will be like this. So now one of the important question related to the LED, that is what we call as internal quantum efficiency. What we call it as internal quantum efficiency. So internal quantum efficiency का मतलब क्या है? So क्या होगा? Internal quantum efficiency क्या करेगा? So out of the total rate recombination, out of the total rate of recombination, what is the portion of radiated recombination? What is the portion of radiated recombination that will give you the clarity? That will give you the clarity. So this is the internal quantum efficiency. So please make a correction here. So this is what we call as internal quantum efficiency. Internal quantum efficiency. So internal quantum efficiency of LED is given like this. Internal quantum efficiency of LED is given as, out of the total rate, what is the portion of radiated recombination? So that is what we call as the quantum efficiency internal. So this is what we call as internal quantum efficiency. Okay, so this is one of the important area where a question can be formed. So now basically what is happening, electrons are ejected and in return they are falling down. In return they are falling down. When they are falling down, photons are released. When they are falling down, photons are released. So we are giving electron hole pair injection. In addition, we are getting the photons release. Electron hole pairs are injected, as an addition photons are released. So number of EHPs injected is giving me number of photons. Okay, so the internal quantum efficiency can be defined as number of photons generated by number of EHPs injected. So the number of photons is 54 into 10 power 10, suppose you take. So the count, that is whatever it may be. So this particular ratio, हम बोलते हैं, this particular ratio is called as percentage of quantum efficiency. Okay, so this is the number of photons generated by the number of EHPs injected. So this is the number of photons generated by number of EHPs injected. Number of photons generated divided by number of EHPs injected, that is what we call as internal quantum efficiency. इसके ऊपर भी क्वेश्चंस आ सकते हैं, नोट कर लो बेटा ये फॉर्मूला. So this is one of the important formulas. ये फॉर्मूलास के ऊपर भी आपको क्वेश्चंस आने की चांसेस बहुत है. एकदम बढ़िया टॉपिक है ये, इसके ऊपर भी हमको क्वेश्चंस आएगा, निकालेंगे क्वेश्चंस को. सो ट्राई टू अंडरस्टैंड दैट. चलो, so that is the internal quantum efficiency. इसके बाद हम लेंगे, so if I'm taking divided by time, so I'm going to get rate. So if I'm going divided by time, so if you divide with the time now, I'm going to get rate of photons, and divide by time now rate of EHP. So this is called rate of photons, rate of EHPs. So rate of photons का units है per second, rate of EHP units है per second. So from the EDC subject, the rate of photons can be taken as, from the EDC subject, rate of photons can be taken as optical power by energy of the photon. Rate of EHP can be taken as I bias by Q. So why? Because if we check the units, power is equal to energy per time, energy gets cancelled, units will be per time. So this is I is equal to Q by T, QQ gets cancelled per time. Okay, so now the internal quantum efficiency, if I am taking this rate of photons by rate of EHP, so rate of photons is P optical by energy of the photon, rate of EHP I bias by Q. So P optical by energy of photon into Q by I bias. So this particular ratio, if you check now, so this particular ratio, so this one is called as P by I, so which is called the responsivity. So responsivity is taken as P optical divided by I bias. P optical divided by I bias. So please make a note of this point. P optical divided by I bias. रेस्पॉन्सिविटी। नाउ इसके ऊपर भी क्वेश्चन देखो। सो इंटरनल क्वांटम एफिशिएंसी इज गिवन बाय P optical energy of the photon into Q by I by S. So responsivity is given by P by I by S. So this is the optical power energy internally. Why? Because this is very important. जो light जो generate हो रहा है वो internally generate हो रहा है. So optical power generate internally bias current supplied. So responsivity को हम क्या बोल सकते हैं? Responsivity को हम sensitivity भी बोल सकते हैं. Responsivity को हम sensitivity इसको हम क्या बोल सकते हैं? Sensitivity भी बोल सकते हैं. So these units are watt per ampere. So optical by I by S, so responsivity units are watt per ampere. So this is the internal quantum efficiency ka formula. Please note down on this formula. Now we will do some questions. Okay, so this particular part is the responsivity. So responsivity Q by I by S. So this is the energy of the photon. Energy of the photon ka formula hc by lambda. So this is hc by lambda. Okay, so internal quantum efficiency is responsivity into Q by hc by lambda. Now इसके ऊपर क्वेश्चंस करवाएंगे वन बाय वन. So try to answer this question, make it fast. he has given 6 into 10 power 6 EHPs are injected for gallium arsenic LED. As written, 5.4 into 10 power 6 photons are generated of lambda. So the lambda is given here. What is the lambda? So the lambda value is 650 nanometers. When the V bias is 2 volts and R forward is 100 ohms, then calculate the optical power generated in internal quantum. So let us do step by step first. So first let us go for the internal quantum efficiency. Let us go for the internal quantum efficiency. So internal quantum efficiency का formula आपके पास है ना? Internal quantum efficiency का formula आपके पास है? You can use that formula. Chalo. So if you see this, so what I can take, 6 into 10 power 6 EHPs are injected. So internal quantum efficiency you can note down. So what is the internal quantum efficiency? So this is the LED. So now they're coming and hitting, they're coming out like this. 6 into 10 power 6 EHPs are injected. Okay. So input is this. So 6 into 10 power 6 EHPs, electron hole pairs, are injected to the LED. As a return, I am getting 5.4 into 10 power 6 photons. So as I told you, the internal quantum efficiency of LED can be taken as number of photons coming out divided by number of EHPs injected. So this is what the optical instrumentation. आपने EHPs को दे रहे and आपको रिटर्न में photons आ रहे. So into 100 करें तो आपको percentage आएगा, लेकिन only internal quantum efficiency means directly you can take number of pH. This is, I can take it as 5.4 into 10 power 6 divided by 6 into 10 power 6. So I am going to get 0.9. Am I right? So I am going to get 0.9. So now if I am taking the complete formula of internal quantum efficiency का complete formula क्या है? So if you see the internal quantum efficiency का complete formula, rate of photons, how many photons are generated for how many electrons? आपने electrons दे रहे, आपको रिटर्न में कांति मिल रहे. So rate of photons can be written as power, optical power of the photon divided by energy of the photon. So as per the mathematics, power is equal to energy per time, energy gets cancelled, so units per second aayega, and divide this rate of EHP. So I can take rate of EHP means current, I am giving current by charge. As per the electronics EDC, I is equal to Q by T, Q gets cancelled, per second आएगा. So यहाँ से आप ऐसा निकाल सकते हैं P opt divided by energy of the photon into, so this is Q by I. This is nothing but I bias. So this is the quantum efficiency. हमको क्वेश्चन पूछ रहा है, is asking the optical power generated. So optical power generated के लिए हमने ये ले सकते हैं, लेकिन energy of the photon को पता होना है. Energy of the photon का basic formula क्या है? Energy of the photon is equal to hc by lambda है. Mathematics और physics का formula, energy of the photon is hc by lambda. So I can write quantum efficiency, RHS को लगाओ, energy of the photon into I bias and Q इधर आएगा. This is the formula for optical power. अच्छा है ना? So फटाफट कर लीजिए बेटा. Energy of the photon को फिर से replace कर लो. Energy of the photon is nothing but hc by lambda. So I can take this as hc and this is I bias by lambda and Q. So this is now optical power. Got it? So this is optical power. So कैसा handle करना है इसको? Step by step कर लो. इसके लिए हमको I bias चाहिए, लेकिन क्वेश्चन में I bias नहीं दिया है. देखो ध्यान से. So what is mentioning? He has given the bias voltage and the forward bias resistance. So I think you can do some electronics. So this is a diode. Am I right? So this is a diode and this is a forward bias voltage. ये है हमारा forward bias voltage. So आपको पता है this is Y bias. So V is given as how much? 2 volts. And remember this diode is having some resistance, forward bias resistance. So the forward bias resistance is given as 100 ohms. Now you can calculate the current ना, basic KVL use कर सकते हैं. So current का formula क्या है? Current of the bias that I can take a Ohm's law, applied voltage by resistance. So this is a forward bias voltage and this is a forward bias resistance. Simple common sense use करना एग्जाम में, बहुत चिंता मत लेना. You should not do world tour while you are doing the problem. Problem करने के समय पूरा attention में होना है, पेपर पर ध्यान रखना है, world tour नहीं करना, अंतर्जातीय विहार नहीं करना. So forward bias voltage is equal to 2 volts and the forward bias resistance is 100 ohms. So I am going to get 0.02 amperes. 0.02 amperes. Now everything is available. You can substitute here. So from this I can substitute this formula use करके मैं कर सकता हूँ ना. So I can take this quantum efficiency into H into C into, okay, so this is my I bias, this is my I bias, this is the lambda and this is the Q. So I can take it off. Now I can substitute the P optical everything. So from the previous question we got the quantum efficiency answer as 0.9, correct है ना? 6 9 is 54, okay, 0.9. So I can take this as 0.9. And H means Planck's constant, 6.625 into 10 to the power of minus 34 ही लेना है इधर. And C is the velocity of light. अगर nothing is given, we have assumed the velocity of light is 3 into 10 power 8 meter per second. I bias आपको calculate कर दिया है. That got you have 0.02 amperes. So you got it as 0.02 amperes. And lambda is the wavelength. The wavelength is given in the question. The wavelength is given as 650 nanometers मेरे दोस्तों. So 650 आप substitute कर लो. So कितना आएगा? 650 into 10 to the power of minus 9 and this is 1.6 into 10 to the power of minus 19 coulombs. So if you simplify, so that is answer. जो भी लाइव में है एक बार मुझे कंफर्मेशन कर दीजिए बेटा, आंसर कितना आ रहा है? Chalo, if you see now, this is 0.9, 6.625, 3.02 divided by 650 divided by 1.6. 10 4 minus 34 plus 8, 10 4 minus 26, 10 4 minus 26 plus 10 4 minus 10 4 2 आ रहा है ना 100. So I'm getting 0.034 watts आ रहे हैं, 0.034 watts आ रहे हैं ना, 0.034 watts आ रहे हैं, 1.6 नहीं है. कैसा 1.6 आएगा? Check it again. 0.9 into 6.625 into 10 power minus 34 into 3 into 10 power 8 into 0.02 divided by 650 divided by 1.6, 10 power minus 9 into 10 power 28. 0.034 watts ना, आपका पता है ना, ये लेस आ रहा है, आपको कैलकुलेट कर लो. 0.034 watts आ रहा है, कैलकुलेशन मिस्टेक है आपका. 0.034 watts is the right answer. Okay, चलो let us go for the next question. Try to answer this question. The radiative and non-radiative recombinations, the radiative and non-radiative lifetimes of minority carriers in the active region of LED are 60 nanoseconds and 100 nanoseconds respectively. Determine the total carrier recombination lifetime and power internally generated within the device when peak emission wavelength is 0.87 micrometers at a drive current of 40 milliamperes. Can you do it? Yes, Rajeshri, you try to do it. These are certain problems on LED. Now we'll go for the some of the interesting things about the LED. Some more LED features. You see the LED features. Actually, LED में जो light generate हो रहा है, so that is internal only. That is always internal only. So this is the. So try to understand the words. जो optical power generate हो रहा है, so this optical power is internal only. This optical power is internal only. Okay. And this is the optical power externally emitted. Definitely this will be less or not, क्योंकि वो LED का फीचर जो सरफेस है ना, LED का जो सरफेस है, सरफेस से बाहर निकल रहे, गर्भस्थान अंदर है, LED का लाइट कहाँ जनरेट हो रहा है, LED का सेमीकंडक्टर लेयर से जनरेट हो रहा है. So please remember this, from that area it is coming. So the light is coming from that smallest part. अब थोड़ा ध्यान से सोच लो. You try to understand this. LED light is coming from that. So जो कांति बाहर निकल रहे, जो लाइट बाहर आ रहे, so that's why always remember light comes from the darkest part. Early morning 4:45, 5 o'clock, if you see the beach, the dark sky, dawn, slowly the light will be coming. So the darkest, from the darkest, very, very darkest part of the life only the light will come. So you have to understand this logic. This is a philosophy. This is what philosophy. So actually light is going to be generated here. So this is the light. So here the optical power is generated. So this optical power is coming out. It has to cross this barrier. So when it is crossing that barrier, na, so जो light आपको मिल रहा है, that will be externally emitted, that will be lesser. So optical power externally emitted will be lesser. So if you see that, so if you see that formula, so this is the formula of that mu x square. Optical power externally emitted is equal to optical power internally generated F into mu naught square by 4 mu x square. So this is the interesting thing. Externally emitted optical power will be divided by 4. So F is a transmission factor. So this is the mu x square. Optical power externally emitted is P internally generated 4. This F is a transmission factor of semiconductor layer. Optical power generated internally, optical power emitted to outer layer. So optical power internally generated F into mu naught square by 4 into mu x square. F is a transmission factor at semiconductor layer interface. Okay, please note down this point. Please note down the doubt lines. So this is optical power externally emitted. Definitely that will be lesser. Optical power externally emitted, that will be lesser. So mu x is the refractive index. Refractive index. That is refractive index. Mu naught is the refractive index of the outer medium. So usually that is air. Mu naught is the refractive index of air. So that will be 1 generally. But जो भी semiconductor है ना, that will be mu x. Okay. So F is the transmission factor of semiconductor layer interface. So P optical internally generated is optical power generated internally. So this is the optical power emitted to the outer side. Obviously आपको ये समझने आना है, externally emitted optical power will be always lesser than the optical power internally generated. ये याद रखना है आप. Okay, so from here I can write like this. So this is the formula. Now if you see this one diode, so this is a PN junction diode, so this is the bias V supply. So now this is the P and this is the N, so this is optical power externally emitted. So electrical power given as input is V into I bias. External power emitted, that is internally generated, F into mu naught square by 4 mu x square. Okay, so there is another formula of external efficiency. What is external efficiency? How much optical power externally emitted to the how much electrical power input is happening there. How much electrical power input. Okay, so please note down this. efficiency जो भी बाहर आ रहे हैं ऑप्टिकल पावर एक्सटर्नली emit हो रहा है, so that you are comparing with electrical here. So this is the external emission and this is electric power. V into I is electric. So this is the electrical power. Electrical power is converted to optical power. So this is the V into I. So this is optical power externally emitted. So optical power externally emitted is this. So now if I am taking this both ratio, optical power internally generated F into mu naught square by 4 into mu x square. So this and if this you compare, that is the conversion. You are giving electrical input, आपको कांति मिल रहा है. So this particular things you have to check it out. Okay, chalo, based on that, there is another efficiency called coupling efficiency. So internally generated is original, जो भी externally emitted है that is lesser, then finally it commits to the optical fiber, that is different. So please note down that. So see here, LED from a gallium arsenic has a refractive index of 3.6. So he has given the gallium arsenic refractive index. So this is mu x. (3.6). Calculate the optical power emitted into air as percentage of internal optical power for the device when the transmission factor for the crystal air layer, this is F. F is equal to 0.68. Okay. So what is asking? First question, calculate the optical power emitted into air. So optical power externally emitted, as I told you, optical power externally emitted will be optical power internally generated, so comparatively will be less by 4. नीचे mu x square आएगा, ऊपर mu naught square आएगा, and here comes the transmission factor F. So that was a formula, right? That was a formula. So what is asking? Express it as a percentage. Transmission factor is given as 0.68. Okay, right? So optical power internally generated is not mentioned. So this is given as 0.68. Air is 1 divided by 4. Refractive index of silicon, that is 3.6, is given. So into 100, if you do, you will get a percentage. So that will be 0.68 divided by 4 divided by 3.6 into 100. 4.72 are na? So 4.72 of P internally generated. Am I right or not? Any mistake? Sorry. Not a mistake. Refractive index is 3.6 square है ना, and F is equal to 0.68. So mistake कर दिया मैंने, calculation mistake कर दिया. Okay, 0.68 divided by 4 divided by 3.6 divided by 3.6, 0.013. So optical power externally emitted is equal to optical power externally emitted is equal to 0.013 optical power internally generated. That means percentage, if you take 1.311 percentage of internally generated. Okay. Okay, what is asking? This is a first question answer. This is a solution for A. Next solution for B, if you take, what is the solution for B? When the optical power generated internally is 50% of the electric power. So optical power generated internally is 50% of electrical power. Optical power generated internally is 50% of electric power. Then what is the external power efficiency? External power efficiency. So that is optical power externally emitted divided by electrical input power. Optical power externally emitted is already we have 0.013 P internally generated. The whole divided by electrical input. Electrical input is like that only, right? Internally generated means 0.013 into this is 50% of electrical input. एकदम बढ़िया क्वेश्चन है ना, quality question. So now this gets cancelled. So 50% means 50 by 100, 0.5. 0.013 into 0.5. So that is coming as 6.5. 65. What is the question asked? What is the optical power externally generated? One second. When the optical power generated internally is 50% of electrical power, external power efficiency. External power efficiency is this only, right? 0.65 percentage. So percentage of external efficiency is 0.65. Am I right? Anybody? Any doubts? Okay. You please take this question as assignment, okay? This question also assignment. These two questions you take it as assignment. बच्चे आते हैं, क्लास को सुनते हैं, जाते हैं। जो भी इतना बच्चे रहते हैं ना, उसको कर्टसी भी नहीं रहते, मिनिमम कर्टसी। क्लास को आने के समय गुड मॉर्निंग बोलना, क्लास को जाने के समय गुड आफ्टरनून, गुड इवनिंग बोलना, थैंक यू सर बोलना। ये ऑनलाइन में कुछ भी रिस्पेक्ट ही नहीं है। फैकल्टी का जिंदगी कैसा हो गया ना, स्लेवरी हो गया। रिस्पेक्ट ही नहीं मिलता है बच्चों से। कंटेंट चाहिए बस। ये ऑटोमेशन हो गया, फ्यूचर में पूरा ऑटोमेशन बनेगा। जो फैकल्टी का पोस्ट है ना, वो ऑटोमेशन बनेगा पूरा। machines will come and teach. ओके, टेक केयर। जो भी डाउट्स है आप बताइए। कल का क्लास में हमने लेजर्स, इंटरफेरोमेट्री डिस्कस करेंगे, क्लोज करेंगे महा रिविजन को। डोंट मिस। सो ऑप्टिकल, अगर आपने एलईडी को ध्यान से अंडरस्टैंड किया ना, आपको फोटोडायोड इजीली अंडरस्टैंड होगा, क्योंकि फोटोडायोड इज अ रिवर्स ऑफ दिस। ओके, फोटोडायोड इज अ रिवर्स ऑफ दिस। थैंक यू।